So let's continue our discussion of Snell's law. We've seen some evidence for the fact that light changes direction when it enters one medium from another. And as we know, there is a quantity that characterizes different substances called Index of Refraction, N. So Snell's law is an equation which says that there are angles in one of two different substances, and the signs of those angles are related with these other quantities called the Index of Refraction. And so, yeah, Snell's law says that, well, for lack of better explanation, n1 sine theta 1 equals n2 sine theta 2, or the product of a substance's index of refraction and the sine of an angle in that substance as measured relative to the normal, equals the same product for a different substance. All right? And what my guys have seen is a figure that looks something like this, where these red lines are wavefronts, and these blue lines are several different rays, of which we can look at one. We look at this one ray here, and we can measure, well, this is an incident angle because this is an incident ray coming at a boundary. Here's a refracted angle because this is a refracted ray leaving a boundary. So what we'll do a bunch of is look at specific instances where a specific ray hits a boundary, and let's look at, well, again, relative to the normal, let's look at these incident angles and refracted angles, and we can again relate them with Snell's law. Okay, so right. Okay, so Snell's law says, if we do a little bit of rearranging, we can write the ratio of n1 to n2 as the ratio of sine theta 2 to sine theta 1. Okay? And here's something where we say, okay, what if n1 is less than n2? All right, so here's medium 1 with index n1, and here's medium 2 with index n2. Well, if n1 is less than n2, now let's leave that for a second. This says that, well, that must mean that sine of theta 2 is less than sine of theta 1, right? If the top is smaller than the bottom, then the top is smaller than the bottom, right? Now, what angles have smaller sines? Because this says the sine of the angle is small. So what angles have small sines? Well, a sine curve does that. So small angles have small sines as you get up to 90 degrees. So that means that theta 2 must be less than theta 1. So if n1 is less than n2, then theta 2 has to be less than theta 1, which is what this diagram shows, right? Here's theta 1, here's theta 2, theta 2 smaller, which means that here in this, we've represented a situation in which n1 is, whoops, I did that backwards, in which n1 is smaller than n2. All right, and in a case like this, this helps us demonstrate this nice little mnemonic device that says, less to more bends toward. All right, refraction on a qualitative sense, and semi-quantitative, works with this mnemonic that less to more bends toward. Well, what the heck does this mean? Well, when we say that in our diagram above here, something happened, something went less to more. Well, notice, we went from a smaller index of refraction, or light went from a substance with a smaller index of refraction, medium 1, to a substance with a larger index of refraction, medium 2. So when we say less to more, we're referring to index of refraction. And really the fact that light is traveling from a substance with a smaller index to a substance with a larger index. Well, bends toward, that part refers to that when that happens, when light travels from a substance with a smaller end to a substance with a bigger end, the light bends toward the normal. Toward the normal. And guess what? The opposite's true. More to less bends away. That's not as fun to say. Simple as that. Less to more bends toward. All right, now, that's a very simplified, just way of talking about a lot of different phenomena. What's happening here? Well, we know that as in this case, right, the bigger that n is, that means the slower the wave speed is. So when waves come from one medium and encounter the boundary with another and slow down, that causes a change in direction, right? So that's the physics behind less to more bends toward. But the less to more bends toward sure is a convenient way to, well, qualitatively identify what happens to a light wave. And also a nice sort of way to check your work when when there's a problem to solve. Okay. Now, in each medium, right, there's 3 different quantities we should be able to talk about, and what changes and what doesn't, what's the same and what isn't. All right. So we've talked about the fact that, wave speed, there's only one thing that controls the speed of a wave, and that's the stuff the medium through which it travels, right? And in this case, that's directly tied to this quantity and the index of refraction. So in each medium, do I have a little checky box thingy about? Nope. Right, wave speeds are different. And most of my folks have seen this applet that shows us, well, that wavelength is different because wave speed is different. For the uninitiated, notice here's an applet in which we can control the index of refraction of 2 different media, medium 1, medium 2. Okay, and what we have here are wave fronts of wavelength lambda traveling at this boundary. All right, medium 1 has an index of refraction we've called 1. Medium 2 has an index of refraction we'd call 2. And watch what happens. There's a lot of funky stuff that goes on here, but the crux of it for this part is, well, for sure, wave speed changes, right? That wave travels a lot slower. That wave front travels a lot slower than it did when it was in medium 1. And because it does that, notice, here is distance between wave fronts, lambda, right? Here is new distance between wave fronts. Well, we'd probably call this like lambda 1, medium 1. We call this lambda 2 in medium 2. And what that says is, well, wavelength changes because speed changes. All right, but if you just plain old look at, let me restart, next. If you look at, it's going to take a while. If you look at the rate at which these wave fronts hit the boundary, and when I say the rate at which the wave fronts hit the boundary, what I'm really saying is the frequency at which they hit, how often they hit the boundary. Well, the boundary is, a place in both media. So, the frequency at each media is the same, right? Ding, ding, ding. It doesn't matter where you are. Right here, ding, at the end of the mouse. Ding. Right? The frequency is the same no matter what. All right, because remember, what does frequency of a wave depends on? Well, frequency of a wave depends on whatever the oscillating source of the waves is. Right? And that doesn't matter what stuff you're in. So frequency is the one thing that stays the same regardless of what substance a wave travels through. But because waves change speed when they travel in different media, their wavelength changes. Okay? Sort of good trivia, but good thing to have your head wrapped around. Okay, so sure, N is C over V. Well, that's our definition of what the index of refraction is. It's the ratio of the speed of light in a vacuum. I'll do this. How about this? V light vacuum, right? And this is V light substance in something other than a vacuum. All right? Well, a couple things we know. One is this speed of light in a vacuum is what we call c, right? And that's, 3 times 10 to the 8th meters per second. V, light in a substance, is always less than c. Always, always, always. Nothing in the universe has ever, will ever, can ever travel faster than the speed of light in a vacuum. And that also says that because c is always greater than v, that n is always greater than 1. Always greater than 1. Greater than or equal to 1, I guess, because n for a vacuum is 1. Greater than or equal to 1, sure. Okay, fine. But what this also says is, remember, this is a wave speed. So is this. So that means we can write this as, let's see, f vacuum lambda vacuum over f, I don't know, substance of, the frequency in a medium with index of refraction n times lambda n. Okay? And, oh, yeah, remember, these frequencies are the same. Okay, so what that means is n, index of refraction, is not only a ratio of speeds, it's also a ratio of wavelengths. So two things. Just remember that one, big N, means two things. One, small speed. Two, small wavelength. Okay? Okay. Now, yeah, if we're going to solve, if and when, yes, you will solve problems involving Snell's law and refraction, two real important tips. One is you always really be careful with this. Make sure that angles that you are using, whether or not you're provided with these angles, the angles that you have to use in Snell's law are always measured relative to the normal. The normal being the perpendicular to the surface at the point where the ray hits the surface. All right. And two is that this is, there's no other way to say this, but you just have to be sure you do it, is, match the angle with the right substance. Just don't mix up your ones and twos in those Snell's law examples. Okay? Here's a couple of qualitative ones. All right? We got light here. All this is air. Everything out here is air. All right? And then here's some glass, which out here means N is 1. Well, remember, N of a vacuum is 1. N of air might be like, I don't know how many zeros there are, maybe that many. It's really close to 1, so we just call it 1. But I guess if we're being smart about it, most of these things you say are like out to 2 decimals or so. But the bottom line is, for sure, N of glass is bigger than 1. I know that. Everything is bigger than 1. Even air, but air is close enough to 1 that we just use 1. All right, so here's a ray of light moving at a speed that's pretty darn close to the vacuum speed of light, c. So what happens when it encounters this boundary? Well, first of all, this is what we call we say it's incident normally. Along the normal. All right, so if we look at this boundary at this place right here, I mean, we can do Snell's law, sure. How about this? N air sine theta air is N glass sine theta glass. But the angles are both 0. Well, at least not both, but the incident angle in air is certainly 0. The angle between this ray and the normal is 0, so the sine of 0 is 0, so that whole thing goes away. Well, N of glass is not 0, but it does mean that the sign of theta glass must be 0, and that means theta glass is 0. So there's no change of direction that happens here. All right, but what does happen, right, is because n of glass is greater than 1, it means that, I got a little animation, watch this. It means that the wave does this, gets there, and then, let me back up, does this, gets there, and then slows down. Can you tell it slows down? I'm a master of anime. Oh yeah, look at that, slow down. Okay, until the light gets to this boundary. Okay, and what happens here is, well, qualitatively at least, we can draw a normal. Yes? And here is our incident angle, which you could call theta incident or theta glass, or theta incident or theta glass. And we go here, right, from glass to air, so this is a more to less. Index of glass, I don't know, maybe 1.5. Index of air, 1. So it's more to less. And it means this thing bends toward the normal. Oh, I haven't said this explicitly, but I should. Refracted rays always cross the normal. All right, so it's this ray started on this side of the normal. It's going to end up on this side of the normal. And in this case, it's a more to less, so it's going to bend away from the normal. Well, if it kept going in the same direction, it would go like this, right? That was the direction it came in at. But it bends away from this normal, so it's got to end up, well, how about, yeah, something like that. And two things happen. Notice, right? Notice, let's go all the way from the beginning. We got a certain speed, we got a slow down, and we got a speed up, which sorry, that's not great, but a speed up, which then makes a change of direction happen. Okay, so our refracted angle here, while this is our incident ray, our refracted ray looks like that. All right, and notice that our refracted angle here, measured relative to the normal, theta air, theta air is bigger than the incident angle. Okay? Well, let's look at the opposite case. You know, the old triangular bubble of air in some water. So, a light ray approaches this boundary for the same reason as before. There's no change in direction, but now this is n of 1. This is an n that's bigger than 1, because everything is. So that means we're going more to less here, and that means that, remember, big N means smaller v, smaller wavelength. So when we go to a smaller n, that means a bigger v. So this wave doesn't change direction, but does change speed. Now it gets to this boundary, and at this boundary we can construct our normal. And now this is, right, a less to more. A smaller n to a bigger n. Ooh, sometimes we say this is more optically dense. Optically dense. It's not saying that, like, stuff that's physically more dense has a bigger index of refraction. I think it's kind of a metaphor? I don't know. Maybe I'm oversimplifying. But optically dense, more optically dense does mean bigger index of refraction. Okay, so remember, the ray has to cross the normal, which means that it can't, like, end up over here on the same side of this normal. It can't do that. All right? So the ray will cross the normal, but this is less to more, so it'll bend toward, right? If it kept going in the same direction it was going, it would keep going this way, but it's got to bend toward the normal. So maybe it does, yep, something like that. Looks fine. And remember, let's go through the whole animation. It's one speed into air, speeds up, back in, it slows down when it goes back out there. Okay, so what you might have is something like, here's an incident ray, here's a refracted ray. Here's an incident angle, which you could call theta air if you want. Here's a refracted angle, which you could call theta water if you want. All right, I usually don't draw this one like that whole original path of the wave thing, but it can help for when you're first looking at these saying, well, what do you mean bends toward? Like I said, sometimes what I like to do is draw that initial direction that the wave was going, and then say, well, which way is away from the normal, or which way is toward the normal? Okay, so there's that. An actual example: a laser beam incident at an angle of 30 degrees to the vertical on a solution of corn syrup in water. Beam is refracted to that crazy angle. What's the index of refraction of the syrup solution? Okay, so here's how many of these simple questions will look. They'll look something like this. Here's the surface of solution. So there's the air/solution boundary. Solution of corn syrup and water. A laser beam is incident at an angle of 30 degrees to the vertical. Well, the vertical does happen to be the normal, which is nice. So here is an incident angle. Oops. Oop. Sure. So here is, I'll call this theta air. And it actually tells us that it bends like this, such that theta solution is less than that. And those are not like right on top of it. I can't move this thing. They're not. They should be touching, but there's some calibration with the board here thing. You get it. And so we want the index of refraction of the solution. So this is a Snell's law solution. N1 sine theta 1 is N2 sine theta 2. Probably more appropriate to say something like N air sine theta air is N solution sine theta solution. Okay, we want N solution. Well, N solution is N air sine theta air over sine theta solution. Notice degrees, working degrees. All right, and I bet you get something like 1.3. That's my guess. So N air, just use 1. So sine theta, sine of 30, sine 30 divided by sine 19.24. Well, 1.5, 1.52 perhaps. 1.52 solution. It's just a ratio. It's not a speed. It's not. There's no units. That's it. B. Go. See you tomorrow, folks.